Okay, we're going to look at another form of the equation of a straight line. So we already know this form when r is equal to, position vector r is equal to a plus lambda b, and that's where a is some point which is on your line and b is a direction which is parallel to your line. So if you imagine you took, you had r was one of your points, and you had a, then that means a to r is actually going to be on your line. Okay, it's going to be parallel to your line, and we know that b is also parallel to your line. So if you did AR cross b, you're going to get 0, because we know that if two vectors are parallel, then their vector product or their dot product is their cross product is going to be equal to 0. So really what you've got here is that's going to be r minus a cross b is equal to 0 is what we're going to get. So that's another form of a vector equation with a straight line. So if you see a vector equation of this form, the a here, whatever's being taken away from the r, is going to be a point which is on your line, and whatever you're doing the crossing with here, so this vector is the direction that your line is parallel to. So in this example it says, find an equation of the straight line which passes through the point a, which is 2 minus 1, 1, and is parallel to I plus 4j minus 3k. Okay, I've got most of the working out done out for you here in this one. It says the position vector of A is 2i minus j plus k. So that's just from here. That was just our point A written out in vector form. So if r is any point on the line with position vector r, then A to r is equal to r minus, and that was your position vector A. And this is parallel to this thing, so I plus 4j minus 3k, so it's parallel to I plus 4j minus 3k. So if you do so AR is parallel to this, so if you do the cross product with AR and the I plus 4j minus 3k, you're going to get 0. So this could be rearranged. If you imagine I've just done my R cross the I plus 4j minus 3k, that's here, and over on the other side then, I've just brought this across, so that was the 2i minus j plus k crossed with the I minus 4j plus 3, and it was minus, so because it comes across the other side, it becomes positive. Okay, to get this in, we need a wee bit of working out how we've actually got to here. So they've skipped this out, so we're going to show how we actually get this bit. So here, I'm just going to do the working out for this up here. So how we actually get this, that is your ijk, and then we had 2 minus 1, 1, and then 1, 4, minus 3. If you do that out, you're going to get I times, and it's going to be minus 1 times minus 3 is 3, and then minus 4, so it's going to be times minus 1, then minus j times, and it's going to be 2 times minus 3, which is minus 6, and then minus 1, which is going to be minus 7, and then plus k, and it's being multiplied by 2 times 4, which is 8, and then minus 1 times 1, so it's going to be 8 minus 1, so 8 plus 1, which is going to be 9, and then if you tidy it up again, that's just me minus I plus 7j, and then plus 9k, and that's it. So that's where that comes from. I just skipped a wee bit of working out there how we got this result here. So the equation of your line is just equal to this thing. So it is 2i minus j plus k plus lambda upon I plus 4j minus 4k. So you can see it's the same thing, same thing as this, but it just looks a wee bit different when you see it. Okay, we're going to look now at equations of planes. Now a plane is just a surface, so your desk is a plane, a board would be a plane, a window would be a plane, a door would be a plane. So it is just a surface in 3 dimensions. So here, we're just going to look at this and see what we have. So this is a plane we're going to be talking about, and we have got, if you imagine you've got a point on your plane A, which has a position vector A, you have some general point R, which with position vector R, and you've got n, which is normal to your plane. So it says the point A with position vector A lies in the given plane. The vector n is perpendicular to the plane. The point R with position vector R is any other point in the plane, or I like to call it the general point in the plane. So A to R is equal to R minus A. And since both A and R lie in the given plane, then AR must lie in the plane. But if n is perpendicular to the plane, then the direction of n and AR must be perpendicular. So if two vectors are perpendicular, then their scalar product is 0. So you have got this was your A to R, and it was perpendicular to your n. So if you do AR dot n, you get 0. So if you just multiply that out, you'll have, or do that out, so you'll have R dot n minus A dot n is equal to 0. And therefore R dot n is equal to A dot n, and this is your equation of your plane. So if A dot n is equal to P, that's just some number, then the equation of a plane is R dot n is equal to P. So that's your general equation, that's your scalar product form of the equation of the plane. So it says, given that a plane contains a point with position vector A and R is a position vector of any other point in the plane, or your general point, and n is perpendicular, the scalar product form of the equation of the plane is R dot n equals P, and that's where P is equal to A dot n. So if you saw R dot I plus 2j minus k, for example, is equal to 6, that is the scalar product form of a plane. You know it's perpendicular to this vector as well, which is important. Okay, we're going to look now at the Cartesian equation of a plane. So going from what we've just done, how we get to the Cartesian equation of a plane, which involves x, y, and z. Okay, this is very, very easy. So consider a plane with the equation r dot m is equal to p, where if your normal is ABC written as column vector, and you write your r, writing the r as, there we are, as x, y, z, then this is r dot n is equal to p. And if you just do that out, remember how to do the scalar product, it's just a product sum of the products of the coefficients of the i's, the j's, and the k's. So x times a, y times b, z times c, or ax, so that's ax plus by plus cz equals p. So thus a plane perpendicular to a vector I plus b vector j plus c vector k has Cartesian equation ax plus by plus cz is equal to p. Okay, one last wee thing on this page. It says to show that a line lies in a given plane, show either that the line and the plane are parallel and they have a common point, or the line and the plane contain two common points. So let's just look at those in a wee second. Okay, the first one, show that the line and the plane are parallel and they have a common point. So you've got, say you have your line and the plane both have this common point here, and they also have the same, they're also parallel. That means they're going to have, the line has to be in the plane. You could have had that line definitely not being in the plane but being parallel to it, but if it has the same point and it's parallel to it, it has to be in the plane. Okay, the next one says the line and the plane contain two common points. So if you imagine you've got a point here which is definitely in your plane, you have another point here which is definitely in your plane, that if your line goes through them, then your line has to be contained within that plane as well. So that's all that they're talking about here. Okay, so in this example it says, a point A with position vector I minus 2j plus k lies in a plane. The vector minus I plus j minus k is perpendicular to the plane. Find an equation of the plane, and then find, first of all, the plane in scalar product form. So your general point R is any point in the plane and has position vector lowercase r. Then this is your r minus a dot n. So r minus a lies in your plane. So that is a directional vector within your plane. N is perpendicular to your plane. So r minus a dot n equals 0. So that's what we've just covered for your scalar product form of a plane. So when you do that out, you're just going to have your r dot this thing, and then on the other side you're going to have this. So really I could add in another wee line in here, just so if I do that out, I'm going to have my r dot minus I plus j minus k, and then I'm going to have minus I minus 2j plus k upon minus I plus j minus k, and that equals 0. And then they've just brought this bit of it across to the other side. That's all they've done. And when you do that out, remember I can only be scalar dot producted with I. So I times I dot minus I gives you minus 1, minus 2I minus 2j dot j gives you minus 2, and k dot minus k gives you minus 1. So that's what you get. So it tidies up just minus 1 minus 2 minus 1 gives you minus 4. So that is the equation of the plane in scalar form. Okay, they ask this next bit quite a bit, and it is ridiculously easy. So all you have to do here is let your r be equal to x, y, z, and then just do your dot product. So your r is equal to x, y, z. So when I say x, y, z, that's a column vector. So it's xi plus yj plus zk. And then you can see it just goes, when you just do the dot product, you just get minus x plus y minus z equals minus 4. And multiply everything through by minus 1, you'll have x minus y plus z equals 4, which is a Cartesian equation. Okay, you could have done this even easier if I looked at this and I did it as a column vector, just to make it a wee bit quicker. I could just write it as a column vector, minus 1, 1, minus 1 equals, what was it, minus 4. And when you do that out, you're just going to get minus x plus y minus z is equal to minus 4. And then multiply through by minus 1 to give you x minus y plus z is equal to 4. So you can do it whatever way you want. Definitely I prefer the column vectors as it's much quicker. Okay, this example says, show that the line with equation r is equal to I plus 2j plus k plus lambda upon 2I plus j lies in the plane with equation r dot I minus 2j plus 2k equals minus 1. Okay, right, to do this, we have to either show that your line and your plane have the same or parallel to the same thing and contain the same common point, or else they have two common points. And I'm going to do this one using two common points. So first of all, I'm going to test out, I know one point which my line definitely has is I plus 2j plus k. Because remember this here, this is r is equal to a plus lambda b, and a is a position vector, a is a point which is on your line. So this I plus 2j plus k hopefully is on my line. So what I'm going to do is I'm going to sub I plus 2j plus k into the left hand side of this equation. So instead of r, I'm going to write I plus 2j plus k. So I know my line passes through I plus 2j plus k. I'm going to sub it in on my left hand side and see what I get. I'm hoping to get minus 1. If I get minus 1, then I know that this point definitely lies on my plane. So I put it in, and when I do the dot product, I get 1 minus 4 plus 2, which is equal to minus 1. So we have shown that the point with position vector I plus 2j plus k therefore satisfies the equation of the plane. Thus, the point with position vector I plus 2j plus k lies on the line, and also it lies in the plane. Okay, I could pick effectively what I've done here to get this point is I put lambda equal to 0. Now I can put lambda equal to any other number. I can put lambda equal to 17, 18, 19, 20, whatever, and then I would find, and then tidy it up, and I would find another point which is definitely on my line. The easiest thing to do is just let lambda equal to 1. So let lambda equal to 1, and you will get, if you take lambda equal to 1, then your r point, so that's I plus 2 times 1, so 2I plus times 1, so that's going to be 3I, 2j plus another j is going to be 3j, and k plus no more k's is just going to be k. So 3I plus 3j plus k lies on your line. So now we've got this point, which we know lies on our line. We want to sub it into this equation, into this left-hand side of the equation of your plane, and hopefully again it equals -1. So we put that in, so 3i plus 3j plus k dot I minus 2j plus 2k is equal to 3 minus 6 plus 2, which, surprise, surprise, it does equal to -1. So this point is also on your line and also the plane, hence the line lies in the plane. Therefore, line and plane contain two common points, and hence line lies in the plane, and that's it. Okay, the last couple of examples here, and we're also talking about the vector equation of a plane. So we've had the scalar form of a plane, we've had the Cartesian form of a plane, now we're on to the vector equation of a plane. So if you've got a point A, which lies in a plane, and R, which is a general point of the plane, and you've got B, which is some directional vector which lies in your plane, and C, which is also another directional vector which lies in your plane. That means R is equal to A plus AR. So to get to your general point R, you have to go along A, and then you have to go along AR. Now you may remember way back when that since any vector can be any coplanar vector, any vector can be written as scalar products of two non-parallel coplanar vectors. So we typically would use, to get this AR, the easiest way to get AR obviously is using your I and your j vectors, but you could use B and C to do it. So AR could be written as lambda B plus mu C. It's an awkward way to do it, but you could do it. So that means your general equation of your point that lies in your plane is A, where A is a position vector of a point lying on your plane, plus lambda B, where B is a vector, directional vector which lies within your plane, plus mu C, where C is also a directional vector which lies in your plane. And that's it. Okay, we're going to look at an example of this one. It's a bit of a strange one. We're going to look at an example here of how we use it. So in this one it says 3 points in a plane have coordinates A, B, and C as shown, referred to an origin. Find the vector equation of your plane. So first thing we need to do is get our directional vectors. So I've gone for A to B and A to C. So these are, and clearly they're two non-parallel vectors which lie in the same plane. So they have just said R is equal to, so they've used I think they've used A just, yep, this is really A. So what this is really, we'll just write out what it is. Really what they've used, R is equal to your point A plus lambda, and I think this first one was A to B, which is definitely a directional vector in your plane, and mu A to C. Now, this, folks, is why it is so important that you set out your work well. The examiner does not want to have to be working, see your answer and have to work through and see if it's possible. Think just how many different versions of this there could be. You could have used A, B, or C as your position vector bit. I've used A and B. I could have used A, B, and A, B, and C, A, or whatever for these. Could have used all sorts of different things. I could have used B, A, and B, C. I could have used CA and BC. I could use lots of different things, so many different combinations. So set it out well so they can clearly see what you're doing, and that's it. Okay, it says find the Cartesian equation of a plane containing the points A, B, and C as shown. So to do this, I want to find the Cartesian equation. Now this is where it gets I find it gets quite tricky. So I'm going to go back and think, what does a Cartesian of a plane actually look like? It's AX plus BY plus CZ is equal to P, is a Cartesian equation of a plane. So your A, B, and C, and X, Y, Z is equal to P. And this bit, this A, B, C, this is the normal to the plane. So I have to write out the equation of the Cartesian equation, general Cartesian equation, and then think, well, what is it? How is this thing actually made up? So ABC is the normal to the plane. So that's what we want to do here. So to find the normal, you imagine you've got your plane. It's got points A, a point B, and a point C. A to B is going to be a position, a vector within your plane. A to C is also going to be a vector within your plane. So they're both parallel to your plane. So if you do their cross product or vector product, you're going to get their normal. So that's what we're doing here. So they found A to B, they found A to C, and then they're doing their vector product. So that it's a determinant of a 3 by 3, remember. First row is just ijk, second row is just this one, so 1, 0, minus 1. And the third row is just this one here, the AC, so it's 1, 1, minus 2. When they've done that out, they've omitted the working out for that, and they've just got ijk. So ijk is normal to this plane. So when you do that out, then what they've done here, this really is just, they've just done r minus a dot n is equal to 0. So they've just used, they've actually used the B point for the for this bit. It doesn't make a difference. You could have used your A, it would have worked out the same. And since they use B, since B is a point which lies in your plane, and when they worked it out, that's what they got. They got x, y, z is equal to 3, and that's it done. Okay, folks, you're now ready to do this exercise, exercise 6c, and we have a list of questions for you to do, which you can confirm with the ones in your notes.